Hi, my name is Bennett Akpomedai, and I would be presenting our research paper titled Energy Efficient UAV Surveillance for Early Wildfire Detection using AI-driven image analysis. And my co-authors are Dr. Atef Shalan, we have Nafil Alam Wali, and Dr. Mushin Rahman. Our table of contents, we'll be looking at our introduction, then our background of the study, our methodology, the implementation of our work, the results and analysis, the discussion, a brief conclusion, and future works, and also the references that were used in working on this paper. Looking at our introduction, it is keen to know that wildfires are becoming more frequent and destructive due to climate change and also land uses. Making early detection critical to reducing is very critical to reducing environmental and economic damage. We know that traditional monitoring methods like satellite towers and also sensor networks they face limitations due to cost, also coverage, and then timelines. So what UAV offer is a promising alternative, but even though we know that existing UAV based systems they consume a lot of energy and they struggle with continuous large scale monitoring, which is needed for early wildfire detection. So for us to be able to address these challenges, our research introduces an AI-powered UAV surveillance system which is designed to balance accuracy with energy efficiency. Our proposed model uses a two-stage approach, which in the first approach, the UAVs perform continuous low resolution monitoring and then switch to high resolution monitoring only when there's a potential fire signal which is being detected. Our custom CNN, which is our convolutional neural network, was trained on diverse data sets, which ensures accurate detection, achieving 83% accuracy and 0.96 when it comes to precision, and fewer false positives. Our energy analysis revealed a 64.4 percentage reduction in power consumption, which is very key in terms of the lasting of the power of the UAVs as compared to continuous high resolution imaging. And this helps to extend the endurance of the UAV. So this dual resolution technique and the AI-driven framework helps to produce and generally provide a scalable, cost-effective, and also practical solution um, alternative for real-time wildfire detection in fire-prone regions. And this helps to optimize part of the trade-offs between accuracy, latency, and energy efficiency in general. Our research, just looking at our background, generally our research addresses the limitations of traditional wildfire monitoring methods. We look at methods like satellites, fixed sensors, conventional UAV models, and we propose an AI-based model, which is an efficient UAV surveillance system. Our approach employs a two-stage monitoring process where UAVs perform continuous low resolution monitoring and then switch to high resolution imaging only when fire signals are detected. This our method reduces power consumption while maintaining detection accuracy, ensuring UAV endurance during large scale and long duration missions. It is very key to note that our study focuses on comparing detection accuracy between single and dual resolution models, and then it analyzes energy trade-off and designs a more suitable UAV wildfire surveillance framework for monitoring. Looking at existing literatures, three key areas have been highlighted. The first one is UAVs combined with AI for fire detection, then also energy efficient UAV surveillance methods and Internet of Things driven multi-sensor system. Previous works have explored multi-UAV coordination, talking about hybrid drones, CNN-based Wi-Fi detection, and also machine learning for energy-aware routing. They've had promising results in accuracy and operational efficiency. However, many studies prioritize detection accuracy or dataset designs, and they often overlook UAV endurance and the balance between energy consumption and imaging strategies. Internet of Things enabled frameworks and real-time dashboard. They further illustrate how UAV imaging can be combined with sensors and visualizations generally. And these visualizations tools enhance situational awareness and rapid decision making in this wildfire context. So the main contribution of our work lies within bridging the gap between detection, accuracy, and energy optimization for wildfire specific monitoring. If we adopt our selective two-stage UAV imaging workflow, our model helps to reduce energy consumption by 64.4% compared to continuous high-resolution monitoring while maintaining that strong detection precision and recall. This balance in our model helps to balance efficiency and also accuracy, and not only extend UAV flight time but also makes the approach more scalable, cost effective, and also practical for real world wildfire surveillance and emergency operations at large. For methodology, we see that our methodology outlines an AI-driven um, wildfire surveillance detection model. This helps to conserve energy through, like we talked about, the two-stage imaging approach. We see that generally UAVs they primarily capture low resolution images for continuous monitoring, and they will only switch to high resolution when the signals are suspected. This process has been simulated using created datasets and also deep learning based CNN models. Our workflow includes image processing, we have the classification, and also confidence-based decision making that helps to ensure accurate detection with minimal human intervention. And also in time, this helps to extend the UAV flight times. Our dataset was carefully curated and was developed from diverse publicly available sources to ensure robustness and adaptability under varied conditions. And these conditions include, but are not limited to, landscapes. We looked at lightning, weather conditions, and also the images were balanced between using fire and no fire cases, just to be sure that it's tested for both when fire occurrences are and when there are no fire occurrences, so we can also juxtapose the detection capabilities. And they were labeled and also annotated with precision. Our CNN model was then designed with multiple convolutional and pooling layers to efficiently extract spatial features while remaining lightweight enough for UAV deployment, and also maintaining a balance between accuracy and computational efficiency overall. In terms of our implementation, the data sets were processed and also divided into training and testing sets. They were augmented with transformations to simulate real-world drone variations. Our CNN was trained using over 30 epochs with optimization techniques to enhance our convergence and also avoid drastic overfitting. Another thing that was key is a super resolution technique called the EDSR model, which was used to upscale the low resolution images into high resolution images, enhancing every detail and improving training quality for better wildfire detection performance, because this was an in-lab research. And finally, our energy efficiency was analyzed by comparing the three scenarios. We had three scenarios which were continuously high resolution imaging, which entailed using high resolution continuously for monitoring. Then we have the continuous low resolution imaging, which was continuously using low resolution for imaging. And then the selective high resolution imaging, which is our approach, which happens to be monitoring with low resolution and then switch to high resolution when needed. The results then showed that the optimized two-stage approach saved 64.4% energy compared to the continuously high resolution monitoring, while it also achieved superior detection accuracy compared to the low resolution alone. This balanced trade-off of accuracy and efficiency just shows a scalable and practical solution for UAV-based wildfire surveillance. Looking at our results, the performance of the proposed two-stage wildfire detection framework was thoroughly evaluated, and this was using both the low and high resolution images to determine the model's ability to accurately just classify wildfire occurrences. And in the low resolution stage, the system achieved an overall accuracy of 80%, with the fire class exhibiting a precision of about 0.87 and a recall of 0.74. The resulting F score was about 0.8, and when you look at the no fire class, it demonstrated a precision of 0.75 and a recall of 0.87. The F1 score was 0.81, and this result just showed that the system is reasonably balanced in terms of its predictions, although the lower image resolution limits the ability to detect certain fire characteristics. It makes the model somewhat conservative in its classification. The macro average and weighted average scores of 0.8 further shows that the balance, while highlighting the trade-off inherent in using lower quality imagery for efficient monitoring, as the case may be. And when we look at the higher resolution images when they were used in the second stage of the framework, substantial improvements were observed in classification performance. The fire class then achieved a precision of 0.96%, while the recall slightly decreased to 0.71%, then maintaining an F1 score of about 0.81. Then the no fire class had a recall which increased significantly to 0.96%, and the precision remained at 0.7%. Then the resulting F1 score was 0.84%. So overall, the system accuracy improved to 83%, with both macro average and weighted average metrics increased to about 0.83%. These improvements just show that the addition of high resolution imagery reduces false positive and also enhances our model's ability to our model's reliability across both classes that we use, and this just also strengthens the overall accuracy and consistency of our wildfire detection. Our confusion matrices and heat map visualizations were used to just further illustrate the difference in performance between the low and high resolution stages. And if you look at the visualizations clearly, they reveal that denser areas of high precision and accuracy, particularly for our fire class, shows that it just shows that the high resolution imagery enables clearer and more confident model precisions and decisions. The heat map complement the numerical results in the fact that it shows how enhanced image detail and how it directly contributes to improved detection effectiveness, especially for when you are trying to distinguish between subtle wildfire features that low resolution images may generally miss. So I think overall, the results confirm that the two-stage UAV-based framework provides a practical balance between energy efficiency and also detection performance. And by leveraging the low resolution monitoring for broad coverage and selectively applying high resolution imaging when potential fire events are detected, it shows that the system enhances accuracy without continuously consuming high energy. The combination of these numerical metrics and visual performance indicators just shows that this approach can reliably detect wildfires in real time while conserving resources. And this in turn offers a scalable solution for efficient wildfire surveillance. For our discussion, we look at the proposed two-stage UAV surveillance framework, and overall it just demonstrates a strong capability to balance wildfire detection accuracy with energy efficiency. Primarily, when operating with low resolution mode and selectively switching to high resolution imaging when potential fires are detected, the system just effectively extends UAV flight time endurance without compromising the reliability of wildfire classification, which is very key for our model. This selective approach just reduces unnecessary computational processing and helps to reduce overworking our UAVs. It then in turn optimizes battery life and then supports continuous monitoring over wide areas, and addressing limitations observed in conventional single resolution UAVs or satellite monitoring methods, which are the traditional methods. The high resolution imaging in the second stage just significantly enhances fire detection precision, reaching 0.96 for the fire class and improving overall system accuracy to 83%. This dual stage approach just reduces the false positive compared to low resolution only monitoring, while it achieves a 64.4% reduction in energy consumption, which is relative to the continuous high resolution imaging. We see that despite these improvements, very small flames or early ignition points may still be challenging to detect during low resolution surveillance, which could delay the earliest possible alerts. So, incorporating additional cues like smoke plum detectors and also thermal imaging is a promising approach to help further mitigate these limitations and enhance early detection capabilities. Environmental variability. Environmental variability also poses another challenge to detecting, to the reliability of detection. I will look at factors like changing lighting conditions, dense forests, look at canopies, fog, and maybe smoke from non-fire sources. It can affect image-based classification performance. And although the curated data set included diverse environmental scenarios which look to improve the model robustness, further data set refinement and additional training will be needed to maintain consistent performance across varied terrains like weather conditions, wildfire type. So additionally, real-time data processing and communication in remote regions, they usually face constraints such as inter, um, intermittent and connectivity and also limited bandwidth because of the range of internet access, and which in turn necessitates the integration of edge computing for timely onboarding of AI interference and alert generation in future works. But when compared to traditional satellite monitoring, we see that UAV provide a faster deployment, which is more frequent local observations and high spatial resolutions. However, we can also see that UAVs are limited in their coverage per unit and require energy efficient operation strategies to be able to maximize operational time overall. So rather than replacing satellites, UAV are best deployed as part of a layered detection network that integrates satellite data, ground sensors, and human monitoring teams. So we can see that generally the two-stage UAV framework offers a practical compromise between detection, performance, and also energy efficiency, thereby demonstrating very strong potential for scalable real-world wildfire surveillance, and in turn while highlighting areas for future improvement and also possibly complementary technology integration in the future. For our conclusion, we see that overall our study just introduces an AI-driven UAV surveillance framework which is aimed at early wildfire detection while optimizing overall energy efficiency of the system. Our system employs a two-stage imaging approach which combines low-resolution monitoring with selective high-resolution capture. Only when the fire indicators are detected, we know that this strategy not only improves detection accuracy but also significantly reduces the energy consumption while allowing UAVs to operate for extended periods and cover large areas without frequent recharging or swap of batteries. The integration of intelligent image analysis just allows the UAV to rapidly and reliably identify wildfire threats, minimizing human intervention and enabling near real-time monitoring. So by leveraging these AI-powered networks, our system can process visual data efficiently, distinguishing between fire and non-fire conditions, and then generate actionable alerts that can be worked on. This just makes our approach both cost-effective and scalable, providing a robust solution for wildfire surveillance in regions that are very difficult to access and maybe monitor through traditional methods like satellite imagery and maybe ground-based sensors, as the case may be. Moreover, the framework that we have demonstrates practicability and also adaptability as it helps to balance high detection performance with energy conservation, which addresses one of the key limitations of conventional UAV monitoring system. The selective high-resolution imaging just ensures precise classification of fire events, then also helps to reduce false positive while maintaining our overall system reliability. In concluding this part, these are AI enhanced UAV surveillance model just represents a strategic advancement in wildfire monitoring while offering a scalable, resource efficient, and also high performance solution. It just also shows that our design makes it highly suitable for deployment in remote areas and high risk areas where early detection is critical for preventing environmental damage, economic losses, and also potential threats to human life while saving energy. Looking at future works, we'll focus on enhancing the AI-powered UAV wildfire detection system to overcome current limitations and also improve real-world applicability. Key areas include integrating multi-sensor data such as thermal and infrared imaging to improve detection in very challenging conditions like smoke, fog, lightning, and dense canopy cover. This multimodal approach just aims to increase reliability and also reduce false alarms from visually similar processes. And also expanding our system to support coordinated UAV swarms is another priority for us. So this just enables a broader area coverage, faster response time, and also redundancy. Our future research will explore swarm coordination strategies to optimize these flight paths and also minimize overlapping coverage and conserve energy, which is also very key for us. Additionally, embedding maybe lightweight AI models on the UAVs will help to improve edge computing capabilities and also reduce dependency on ground stations, lower bandwidth usage, and also minimize latency, particularly in areas where they are remote and also intermittent connectivity is lacking. Our further improvements look to also target error handling in terms of false alarm detection and also ethical deployment, which is very key. We have to also frame our work in such a way that it is in line with the standards and also the laws of the land, as the case may be. Our future models will basically leverage multimodal features and also post-processing techniques that help to distinguish wildfire signals from environmental noise, and while privacy preserving measures will help us to ensure that UAV imagery is collected responsibly and restricted to only environmental monitoring rather than just trying to do other surveillance, as the case may be. Real-world field testing across diverse terrains and conditions will help us to validate system robustness, also operational efficiency, and then scalability for large-scale wildfire surveillance. Um, Overall, pursuing these advancements, the system has the potential to evolve into a reliable, ethical, and high-performing UAV surveillance network. And when integrated with satellites, ground sensors, and maybe human monitoring teams, it could significantly strengthen global wildfire detection and response, and also offer a scalable and energy-efficient solution for early warning and also environmental protection at large. Um, our references and thank you to the authors which materials were used in this work, and thank you for listening to our presentation. Have a good one.